Hello, my name is Negar Pouya and I'm currently in my final semester of electrical engineering at Amirkabir University of Technology. I'll be presenting a research project named FiReT, or a Neural Radiance Fields Framework for wireless field reconstruction and transmitter placement, which we conducted at the Microwave Measurements Research Lab at Amirkabir University, and this project was recently published and presented at IKT 2025 and IEEE Indexed International Conference. Wireless connectivity has become essential in our everyday life, from Wi-Fi to 5G systems, but real-world deployments still suffer from dead zones and dropout and throughput regression. Traditionally, engineers rely on site survey that requires dense signal measurement, and these are time-consuming and costly and often infeasible. Our goal was to create a data-efficient deep learning framework that can reconstruct the wireless radiation field from only a few sparse measurements, and also determine the optimal transmitter placement to ensure the best overall coverage. To achieve this goal, we were inspired by Neural Radiance Field, or known as NRF, a breakthrough model in computer vision that reconstructs 3D scene from a few 2D images. However, transferring this idea to wireless propagation is extremely challenging because RF signals are complex valued. They have both amplitude and phase, and unlike light, they interact strongly with the environment, such as diffraction, absorption, reflection, and other things. We first used a NeRF paper dataset for our work, which contains a realistic indoor environment like bedrooms, office, and conference room. And then we modified and extend this dataset by generating new transmitter position, which allowing us to study more about how transmitter placement affects on overall coverage. Our model represents wireless radiation field as a continuous direction error function that assigns to every spatial point the signal it would radiate in space. And the model receives a 5D input consist of spatial coordinates x, y, and z, and direction of arrival theta and phi. Its output is three quantities: A for amplitude, psi for phase, and sigma for density, where sigma indicates how likely each spatial point is to act as a virtual transmitter. We use a residual film MLP to achieve this goal because it keeps the learning stable with the residual connection and maintain directional sensitivity through the network depths using film. Unlike the NeRF baseline, where the DOA is concatenated only once at the input, in FiReT we inject the DOA information through all layers of the network using feature-wise linear modulation, or film. As you can see on the formulation in a slide, the conditioning branch maps the DOA to two modulation parameters, delta 1 and delta 2. Then each layer's feature, denoted by H, are updated as shown in the formula of the slide. And here's delta 1 and delta 2 acts as DOA dependent gates. They adaptively scale and shifted each feature based on direction, allowing the model to focus on the most relevant spatial feature without increasing the model size. At the head of the network, FiReT produces sigma. This sigma, or density, also determines how much each sample point is in a space, contributes to the overall wireless field, and similar to NRF, where T and alpha describe transmittance and opacity. We define them mathematically, as you can see on the slide. Here, T sub I represents how much of the signal is transmitted up to the I sample, while alpha sub I indicates how much of it is absorbed or emitted at that point. The corresponding sample weight is then computed as T times alpha, as you can see, and this weight quantifies the contribution of each sample point to the final channel response observed at the receiver. Then at the output of the network, as you can see, FiReT produces imaginary and real for each receiver channel as the final complex output. Finally, the channel at the receiver is obtained by aggregation the weighted complex signal from all sample points along each backtrace ray. Moreover, another key contribution is our DOA-guided raycasting strategy. Instead of blindly sampling all possible directions, which would be memory intensive, we use DOA estimates from an antenna array to guide the backward ray tracing process along the most significant direction. This greatly reduces the training time and ensure faster and more stable convergence. In this way, FiReT captures both direct and multipath components, include the reflection and it providing a more accurate and physically consistent channel reconstruction. Moreover, using FiReT prediction, we can efficiently optimize transmitter placement. We rank candidate transmitter location based on two metrics. First, number of effective rays reaching the receiver, which represent coverage quality, and second, average channel frequency response or CFR over all receiver, which indicates signal strength. The best transmitter position is chosen as the one that maximizes a combination score of these two metrics. We trained FiReT using coarse-to-fine hierarchical sampling similar to NERV. The model was evaluated on multiple indoor scenes, each contained 500 to 975 receiver points, and finally evaluated the model using the error function shown in the slide. Our result shows that FiReT can accurately reconstruct the wireless field from sparse measurements and generalize to unseen receiver location. In terms of performance, FiReT outperformed the baseline or NeoRF model by a large margin. The baseline model achieved an SNR of 13 decibel versus FiReT reached 21 decibel. It means an 8 dB improvement in reconstruction quality, and moreover, FiReT achieved this performance in only 1/4 of training time, like about 1.5 hours compared to 6.5 hours. Overall, FiReT represents the first NeRF-inspired framework that jointly addressed wireless field reconstruction and transmitter placement using sparse data. We believe this work opens a new path for AI-guided wireless networks planning and partially for Wi-Fi and 5G systems in complex indoor environments. Thanks for watching.